Sheet resistance is a measure of resistance of thin films that are nominally uniform in thickness. It is commonly used to characterize materials made by semiconductor doping, metal deposition, resistive paste printing, and glass coating. Examples of these processes are doped semiconductor regions, and the resistors that are screen printed onto the substrates of thick film hybrid microcircuits. The utility of sheet resistance as opposed to resistance or resistivity is that it is directly measured using a four-terminal sensing measurement. Calculations. Sheet resistance is applicable to two-dimensional systems in which thin films are considered as two-dimensional entities. When the term sheet resistance is used, it is implied that the current is along the plane of the sheet, not perpendicular to it. In a regular three-dimensional conductor, the resistance can be written as, whereas the resistivity, is the cross-sectional area and is the length. The cross-sectional area can be split into the width and the sheet thickness. Upon combining the resistivity with the thickness, the resistance can then be written as, whereas the sheet resistance. If the film thickness is known, the bulk resistivity can be calculated by multiplying the sheet resistance by the film thickness in cm. Units. Sheet resistance is a special case of resistivity for a uniform sheet thickness. Commonly, resistivity is in units of IV unregistered trademark cm, which is more completely stated in units of IV unregistered trademark cm2 per centimeter. When divided by the sheet thickness, an unregistered trademark 1 per centimeter, the units are IV unregistered trademark CMA and registered trademark, cm equals I copyright. The term, centimeter per centimeter, cancels, but represents a special square situation yielding an answer in ohms. An alternative, common unit is ohms per square, which is dimensionally equal to an ohm, but is exclusively used for sheet resistance. This is an advantage, because sheet resistance of 1 AI copyright could be taken out of context and misinterpreted as bulk resistance of 1 ohm, whereas sheet resistance of 1 AI copyright/SQ cannot thusly be misinterpreted. The reason for the name ohms per square is that a square sheet with sheet resistance 10 ohm square has an actual resistance of 10 ohm, regardless of the size of the square. The unit can be thought of as, loosely, ohms or unregistered trademark aspect ratio. Example, a 3-unit wide by 1 unit tall sheet made of material having a sheet resistance of 21 AI copyright/SQ would measure 63 AI copyright, if the 1 unit edges were attached to an ohmmeter that made contact entirely over each edge. For semiconductors doped through diffusion or surface peaked ion implantation, we define the sheet resistance using the average resistivity of the material, which in materials with majority carrier properties can be approximated by. Whereas the junction depth, is the majority carrier mobility, is the carrier charge and is the net impurity concentration in terms of depth. Knowing the background carrier concentration and the surface impurity concentration, the sheet resistance junction depth product can be found using Irwin's curves, which are numerical solutions to the above equation. Measurement. A 4-point probe is used to avoid contact resistance, which can often be the same magnitude as the sheet resistance. Typically a constant current is applied to 2 probes and the potential on the other 2 probes is measured with a high-impedance voltmeter. A geometry factor needs to be applied according to the shape of the 4-point array. 2 common arrays are square and inline. For more details see Van der Poel method. Measurement may also be made by applying high-conductivity busbars to opposite edges of a square sample. Resistance across a square area will equal I copyright/SQ. For a rectangle an appropriate geometric factor is added. Busbars must make ohmic contact. Inductive measurement is used as well. This method measures the shielding effect created by eddy currents. In one version of this technique a conductive sheet under test is placed between 2 coils. This non-contact sheet resistance measurement method also allows to characterize encapsulated thin films or films with rough surfaces. A very crude 2-point probe method is to measure resistance with the probes close together and the resistance with the probes far apart. The difference between these 2 resistances will be the order of magnitude of the sheet resistance. See also, ESD materials, References. General references, Van Zandt, Peter. Microchip fabrication. New York, McGraw-Hill PPA 431 A-2. ISBN A0-07-135636-3 Jaeger, Richard C. Introduction to Microelectronic Fabrication. New Jersey, Prentice Hall PPA 81 A-88. ISBN A0-201-44494-1 Schroeder, Dieter K. Semiconductor Material and Device Characterization. New York, J. Wiley & Sons PPA 1 A-55. ISBN A0-471-24139-3A.